it's 10:20. All right, very good. Cool. Okay, so welcome back, everybody. Yeah, and so this session, our first speaker will be Abhinav Banmareddy. He'll be talking about on testing and robust characterizations of convexity. Yeah, so if you're ready, Abhinav, go ahead.
Thanks, Mary, for the introduction, and thanks everyone for being here. And I'm Abhinav. I'm going to talk about our paper on testing and robust characterizations of convexity. This is joint work with Eric Blake. Let me start the talk by introducing the problem of geometric convexity testing. The problem statement is really simple. So how efficiently can we determine if a body is convex or epsilon far from convex correctly with probability 2/3? This question was first asked by Rademacher and Bempala in the year 2004, but unfortunately, not much progress has been made on this problem since then, and the problem still remains widely open. We are hoping after our paper, there'll be more people interested in the problem, and then we make satisfactory progress pretty soon. So let me, and then over the next few slides, I'll be defining the terms in the above statement so that it becomes clear for people what the model is, what the setting is, and what we are actually talking about. And before that, so you guys might be wondering what I mean by body. By body, I just mean a compact set. So you can just think of it as a set. And all throughout this talk, we'll be dealing with sets in n-dimensional space. So we are dealing in higher dimensions, and you can think of n to be a really large number. So what do you mean by a convex body? We say a body is convex if this is the first characterization, that you take any 2 points. If the line joining the 2 points lies completely inside the body, then the body is convex. And we say it's not convex if there exists 2 points where the line joining the 2 points goes outside the body. And we can extend this characterization to any number of points. So here you take any number of points from within the body, and if the convex hull is contained inside the body, then the body is convex. And if there exists a set of points such that from the body such that the convex hull goes outside the body, then the body is not convex. So I hope the definition of convexity is clear. And next, what do we mean by far from convex? So this here is the formal definition, but what it essentially means is a body K is epsilon far from convex if to make it into a convex body, we have to change at least epsilon fraction of its volume. That is, let's say the volume of K is V, and if K is epsilon far from convex, to change it into any convex body, the total volume you delete and the total volume which you add to make it a convex body is epsilon V. So you need to make lots of changes to make this body convex. Then you say it's far from convex. And then what do we mean by, so what is efficiently? So for that, first we have to define what is the setting we're dealing with and what is the access model. So here the body is unknown to you. You're just given access to 2 oracles. One is the random oracle, which whenever you query the random oracle, it gives you a point uniformly at random from the body. And a membership oracle, you query the membership oracle on a particular point. And if the point is inside the body, it tells you it's inside the body. If it is outside, it tells you it's outside. And so here, by efficiently, we mean the number of queries. So we measure efficiency in terms of number of queries. So now that we know what the access model is, we could probably pause for a few seconds and probably come up with algorithms ourselves. So we are given this body, we don't know if it's convex or not. We have these 2 oracles, a random oracle and a membership oracle. What do we do? So how do we query? Probably the first thing, so after a few seconds of thought, probably the first thing that will come up to our mind is, yeah, we've seen these 2 definitions of convexity. Why don't we just you use those to come up with a tester. So there are, I'm sure most of the algorithms you guys have come up with would be similar to one of these two. So let me define what these algorithms are. They're really simple and straightforward. So the first one is the line test, where you pick 2 points uniformly at random by querying the random oracle, and then just using the membership oracle, you check if the line joining those 2 points belongs to the body. You repeat that a bunch of times, and if you find a violation of convexity, then you say the body is not convex. And even after repeating for a lot of times, if you don't have a violation of convexity, you output the body is convex. So this simple line test, the first result of our paper, or an implication of the first result of our paper, is that the line test is not efficient. So we give an example of a body that is far from 1/8 far from convex, but you take any 2 points uniformly at random, the line lies completely inside the body. So for large n, you can think of this as almost 0. So with probability 0, the line goes outside the body. So what this means is the query complexity has to be exponential for the line test to work. So it's not really efficient. Then the next question to ask would be, what about the convex cell test, the other natural test? So it's kind of an extension of a line test. So it's pretty similar. You start, instead of starting with 2 points, you start with a set of points, and you check using the membership oracle. Using the membership oracle, you check if the convex cell lies inside the body or if it goes outside the body. In lower dimensions, this algorithm has shown some promise, and there have been a few papers on this in 2 dimensions. But in our paper, we show that even this natural algorithm doesn't work. Like, you cannot get an efficient algorithm out of that. So we show a body that is far from convex, and even if you take exponential number of points uniformly at random from the body, the convex hull joining those points goes outside the body with almost 0 probability. So it's not just 2 points. Even if you take exponential number of points, the convex hull is pretty much inside the body. So that eliminates the second natural test as well. And so this is the summary of our results. What we have essentially proved in these 2 theorems is the first 2 characterizations we have seen, the line characterization and the convex hull characterization, they're not robust. So the first theorem says there are bodies that are actually far from convex, but they almost satisfy the line characterization always. And the second theorem says there are bodies that are far from convex and almost always satisfy the convex hull characterization of convex. So both these characterizations are not robust. This is pretty much the end of the talk, and I'll leave you guys with a couple of open questions. The first one is the most important one. Can you solve this problem using polynomial number of queries in membership oracle and random oracle? From what we have seen in the previous slides, if we can do that, the algorithms have to be, we need to come up with innovative ideas which are radically different from what we have seen before. And the second question is, are there other characterizations of convexity that are robust? This is also linked to the first question. If you could come up with a characterization that is robust, then that could probably lead us to a tester. Yeah, that's the end of the talk. Thank you.
Thanks. So we have time for maybe one very quick question, if anyone has a quick question.
Where do I see the questions?
So they, good question. If you have a question, you can put it in the chat box, and then they can be viewed there, or else just unmute yourself and ask. I guess I have a real quick question if you can answer in a minute. Can you give like maybe like a super high level idea of like what does your counterexample look like? For example, the line test.
That's my last slide. I was expecting that question. So it's an n-dimensional body, and so this is an n-1 dimensional ball of radius 1.1, and this is an n-1 dimensional ball of radius 1.1, and at the center you have an n-1 dimensional ball of radius 1, and it's just the convex cell of these three. So here you take the convex cell of the left part and the convex cell of the right part. So it's kind of like the left one is a truncated cone and the right body is a truncated cone. We call this the union of two truncated cones. At the first sight, it doesn't look far from convex, but in fact it is, and the proof is really simple and elegant. I would like you guys to go and look at the paper for that. I think that's the end of the time. Okay.
Awesome. Thanks. Okay, so I guess we're out of time for this. So thanks again. Next up, we have Jonathan Scarlett. Jonathan, are you here? Great. Yeah, so next we have Jonathan Scarlett, who's going to talk about joint work with Eric Price, a fast binary splitting approach to non-adaptive group testing.
Thank you for the
Jonathan,
introduction. Yeah, you can hear me, right? Can you hear me?
Yes.
Okay, great. So yeah, as Mary said, this is work on fast group testing algorithms joint with Eric Price. So for those who are not familiar, I'll give a very quick introduction to group testing. If we imagine we have a number of flasks where a few of them, let's say a small number of them, have some contamination. And we have, say, some testing device where we can put in some liquid and to detect whether it's contaminated. So of course, the simplest thing you could think of is to test these one by one. The idea of group testing is basically testing things one by one when this contamination is rare is actually a bit wasteful. And perhaps we can actually get away with much fewer tests if we group these together. So in this application, grouping them would just be mixing the liquids together and then putting it in your testing machine. So then, for example, with the second test, there's no contamination among the three. The machine returns clean, and you've used one test to rule out these three items rather than using three individual tests. So the savings might not seem great in this toy example, but as you get to more items, and particularly when your proportion of contaminations is low, you can have very considerable savings. As you can probably imagine, the big application of this recently is COVID testing. It has had some amount of success at least, and there's all sorts of other interesting applications. I won't be talking about applications, I'll be talking about the theory. So this is a quick summary of existing results. Most results have just focused on how many tests you need. So the number of tests you can basically think of as k log n, when you have k, you could call it contaminated or defective or infected, depending on your application, and n is the total number of items or individuals. So yeah, think of the optimal bound as k log n, although you could say k log n over k, depending on the regime. In most fast regimes, we could just call it k log n. The algorithms getting this, basically, vast majority have linear or higher decoding time, say between linear and quadratic typically. And there's been a recent line of works trying to actually bring that down to a close to optimal decoding time, which can actually be sublinear in the number of items. There's also been a lot of work on the implied constant in this number of tests, but in this work, we're just focusing on scaling laws. So among these sublinear time algorithms, the state of the art is basically k times log n, or if you're willing to adopt a word RAM model of computation, you could even say Saffron's decoding time is k log k. But these come at the expense of blowing up the number of tests by log k. So number of tests is suboptimal. There's been a couple of more recent works which have brought down the number of tests, almost down to k log n in this work by Inanadol, and then exactly down to k log n quite recently. But these works have a higher decoding time, k squared or k cubed at least. So basically it was an open problem to get k log n in both number of tests and decoding time. And that's what we've managed to solve in this paper. I forgot to mention, this is all for the so-called for each recovery guarantee. So you can think of that as just allowing a small error probability. If you want things to work perfectly for any sort of set of k defective items.
Jonathan, sorry, yeah. I'm sorry to interrupt. I thought it was just me, but it seems like other people are having this as well. It looks like you're sharing only the PDF window and not the presentation window. Oh, there it goes.
Okay, I'm sorry about that.
Yeah.
Okay, so you probably didn't follow all of this summary. Yeah, thank you for interrupting.
All right.
So this was a summary. Number of tests could be, runtime can be as low as k log n, or a bit lower with the word RAM model, but the number of tests has to increase. Then you can get this nearly, well, this optimal number of tests or optimal scaling, but with at least a k-squared term. And in this paper, we managed to get k log n in both. And I was just saying, if you want the for all style guarantee, you actually need k-squared scaling as opposed to k log n. So the for all recovery is much harder, and we don't consider that in this paper. I think I'm very short on time, but I'll try to give a very quick overview of the method. We basically grouped the items in a recursive manner. So you can think of this last layer as being individual items, second last as being groups of 2, then groups of 4, groups of 8, and so on. And basically, we're trying to have the algorithm, we're doing some tests at each of these levels, and we're trying to have the algorithm work down the levels and try to keep track of which of these nodes could be defective. So you're always going to keep the defectives, but then you might keep a few non-defectives. We try to control how many we actually keep and try to keep it small. So this is sort of describing that. We sort of randomly place each of these larger groups into into one of order k tests. So the total is order k log n over k, because there's log n over k levels. There's actually log n levels in this picture, but we can sort of start at level, we could start a little bit down the tree and have log n over k levels. We work down, keeping a list of what we call possible defectives. And our key claims are that by the end, we will keep all the defectives, and we'll keep at most order k non-defectives. So we'll only have very few sort of false positives, so to speak, by this final stage. And you can sort of view this as like traversing a tree, but trying to discard some of the non-defective nodes as early as possible, so you don't have to keep so many items by the end. In a parallel work, these authors actually gave basically the same idea, and that's a very nice paper to read as well. Once we have most of these items discarded, we're left with the defectives plus some non-defectives which have managed to remain. But we can basically resolve that remaining uncertainty using very standard methods, just like an extra order k log k tests will resolve all of that remaining uncertainty. And this whole procedure is entirely non-adaptive. We don't need to see any test outcomes before designing the future tests. We can design all the tests in advance. The way I've described this algorithm, it has a bit of a disadvantage of, well, I said order n storage. I should have said omega n, actually. It requires at least linear storage as I've described it. But if we sort of interpret this idea of placing randomly into tests using hash functions instead of completely independent mappings, then we can basically bring the storage down very low as well. The storage up to some like log factors. I mean, the storage is basically k log n if you use the right hash function. So we can get low number of tests, low decoding time, and low storage. So that's summarized in the table, although not so much the storage part. For the storage part, we found order log k-wise independent hashing to suffice. And yeah, obviously, most of you probably know that requires much less storage than fully independent hashing. And finally, at the end, I've listed a couple of problems for future work. So I'll leave it there, and maybe there's a time for one very quick question.
Thanks. Are there any questions? Again, you can either just type your question in the chat or unmute yourself and ask. I guess I have a quick question. So these results are in the sort of for each non-uniform model.
That's right.
Is there hope of getting a similar result in sort of the uniform model using these techniques?
Yes. So these guys did that.
Okay.
And we did not.
Got it.
Yeah. So yeah, I think they get like close to optimal results there as well.
Very cool.
Actually, I should be careful. Like, they get it for list decoding. Actually, they don't. I don't know if they actually get that for exact recovery, but there's actually well-known techniques for converting from list to exact anyway.
Got it. Cool. Thanks.
Okay.
Okay, so I think that's probably it for time. But thanks again.
Thank you. I'll stop sharing.
Thank you.
Sorry for the technical mess up.
Yeah, I'm sorry for not alerting earlier. I saw it was stuck and I was like, oh, it's probably just me.
No problem.
So thanks to Ella in the chat for pointing out that it was not just me. Yeah, so next up, who is our next speaker? Hendrik, is that you? Great. Yeah, so next up we have Hendrik Fitchenberger, who's going to talk about testable properties in general graphs and random order streaming. Take it away.
So this is joint work with Arthur, Pan, and Christian. And let me just give a very quick introduction into property testing. So in property testing, we are interested in relaxed decision problems. And the relaxation we do is the following. Instead of asking, does some object have a property, for example, is a graph planar or non-planar, we introduce some gap between yes and no instances. So what we want is that, for example, for planarity, a property tester still accepts planar graphs, but we introduce a little gap when it comes to non-planar graphs. And this gap we introduce by defining an edit distance. And the edit distance we define is the number of edge edits we need to make a graph have a property, for example, planar, normalized by the size of the graph. So the number of vertices plus the number of edges. And if this, then we have a parameter epsilon, which says if we need more edge edits than epsilon, then we call a graph epsilon far from being in the property, and otherwise we call it epsilon close. Now, the property tester should just decide whether a graph has a property or whether it's epsilon far from a property with some probability like 2/3 constant probability. And if a graph is epsilon close, for example, the second graph from the left, there's only one edge which makes it non-planar, then the property tester is allowed to answer arbitrarily. And we can have these property testers in at least two flavors. One is one-sided error and one is two-sided error. And the difference is just that if it's one-sided error, we always want to accept objects that have the property. And property testing happens in the regime of sublinear algorithms. So we are interested in reading as few from the input as possible. So the complexity we measure property testers used to measure property testers is just queries to the data structure. So for example, the number of neighbors of a vertex in an input graph we ask for. And here's just one quick definition I'll need later on. When I talk about property testers, I often talk about so-called Q-disks or Q-hop neighborhoods. And that's just the following. For every vertex in the graph, we define the Q-disk of a vertex V just as the subgraph that is induced by a BFS starting at V of depth Q. So you could call this a truncated BFS or just the Q-hop neighborhood or Q-disk or whatever you like. And for example, in this figure, you see the one disk and the two disk of the red vertex. The one disk is the blue thing, and the two disk of the red vertex is the blue and the green subgraph. Okay, so what are our results? So in property testing, some of us care a lot about property testers with constant probability, constant query complexity. So that's in some sense very interesting because for decision problems, you almost always have a linear lower bound because, right, you need to read the whole input to decide something. And there are some property testers which can test with just constant query complexity, meaning you only need a constant portion of the input, no matter how large the input is. And the first result we have is the following, that for general graph, that means any graph with no restriction in the so-called random neighbor model, that is, your algorithm might specify a vertex and ask for a random neighbor. So you have, if you want probabilistic access to the adjacency list of the graph, so that in this model, every property tester can be transformed into the following algorithm, a kind of canonical algorithm. It obtains first a uniform sample of Q-disks, and then it colors these Q-disks. It colors all high degree vertices in these Q-disks with a constant number of colors, and then it rejects if and only if it sees some forbidden set of colored Q-disks. And the forbidden set is, of course, characteristic for the property. Previously, this was only known for bounded degree graphs, and now you might ask, okay, why is this interesting, and why is this harder than bounded degree graphs? Let me just quickly explain. For bounded degree graphs, you can almost always assume that if you just sample 2 Q-disks, then these Q-disks, if they are random, starting at random vertices, they are disjoint, because bounded degree graphs have bounded degree, and so it's very unlikely that that you'll see the same vertex twice. So this gives you, if you see 2 K-disks, this basically gives you bijective decomposition. You know, if I see these 2 Q-disks, then this will be the BFS I've explored. In general graphs, Q-disks may actually intersect because they are high degree vertices which have linear degree. So it's not clear whether, if you're just given 2 Q-disks, these result from 2 BFS which do not intersect, or if they result from 2 BFS which intersect. And that's basically the main difference between bounded degree and general graphs for constant query testers. And the second result is an application of the third theorem. And basically this says that every property tester for general graphs in the random neighbor model with one-sided error and constant query complexity admits a log-n space random order streaming tester. And random order means we are in a streamer model where edges are streamed to the tester in uniform random order. And previously this was known for bounded degree graphs. So there's a similar characterization for random order streaming, similar reduction for random order streaming testing in bounded degree graphs. And for general graphs, this was only known for some graph parameters. And an open problem here is, you see in the theorem, it says one-sided error, and an open problem here is, of course, to do this for two-sided error. And that's it. Thanks.
Thanks. So are there any questions? We have a few minutes for questions. So you can, if you have a question, you can put it in the chat box or just unmute yourself and ask. Okay, so if there are no questions, I guess let's thank Hendrik again. So I'll clap audibly, everyone else can clap. No, unmute yourself to clap if you want, but I'm sure everybody's clapping. So thanks very much. Yeah, so I guess we have a minute and a half before the next talk is supposed to happen. So if the next speaker can set up.
Yeah, so on the schedule, it says my talk's supposed to start at 11 o'clock, but I assume it's, or at 11, but I assume it's starting in 1 or 2 minutes.
Yeah, let's say 10:50, given that 11 is also scheduled as break. So we wouldn't want to have to slot you against break. That would be a very tough.
Yeah, that's a typo on my part. Sorry.
I didn't even notice that. Okay, so I guess we can get started. So the last talk of this session is about the Gaussian sketch for almost relative error kernel distance by Jeff Phillips and Wai-Ming Tai, and Jeff will give the talk. So go ahead. Oh, Jeff, you're muted.
Let me unmute. Okay, great. So thanks. So this is joint work with my recently graduate student, Wai-Ming Tai, and so this is about so I think this as a problem in day analysis, you have you have a set of points in RD, and you want to do some standard day analysis, PCA, so regression, classification, so k-means clusterings, but the linear version of all these sketches aren't working as well. So the typical way to make them so they're nonlinear is to use the kernel trick in machine learning. And basically you go into these algorithms and you replace this inner product, linear inner product operator with a more general kernel instead. And so this is quite common in machine learning. Common kernels, most common ones are the polynomial kernel or the Gaussian kernel. So sometimes referred to as the radial basis kernel is this an example of one. And so we'll focus on the Gaussian kernel in this talk. And the Gaussian kernel, it is positive definite. And what we'll use from that is that this implies that we can represent it in this vector space, where it's a function space where you map every data point with the kernel operator to a function. And think of this as a lifting map into this space. And then you have an inner product in this space. The natural inner product now in this space kind of takes these two functions, and it's actually just the kernel between those two data points. And so this is basically why the kernel trick works. There's this mathematical kind of way of viewing in this RKHS, where it's effectively linear in this space. For day analysis, we don't just want to do this with points. We want to do this with these 2 point sets instead. And so we need this generalization of this, which is these functions are now just the average of all the data points. So these functions are like the kernel density estimates instead of just the kernel functions. And you can define then a similarity or an inner product between these 2 point sets is just the inner product between the averages, right? And then in this talk, so typically in machine learning, this is what people stop and look at most of the time, but there's a natural distance as well. So if we start with the Euclidean distance, we want the corollary of this, which is just using this generalized inner product between point sets. And I can write down the squared distance function this way. And so in any finite dimensional kind of linear subset of the space, it's the Euclidean distance. I call it the kernel distance. Other people call it maximum mean discrepancy or the current distance, depending on the community you're working in. So this this is applications within day analysis, 2 direct applications. One is the kernel 2 sample test, which is where you have 2 point sets and you want to say, are they from the same distribution? And kind of just testing this distance is kind of a recently very popular hypothesis test. And then you can just do all the points on shapes. And this is kind of, you can use this for, say, locality sensitive hashing between these shapes in some nice ways. But the issue with this, although it has no alignment properties, it still requires basically n squared. I have to do this all pairs comparison. I have to do this kernel function for all pairs of points in both the point sets. So what we want to ask in this talk is, can we do an approximate mapping f hat so these distances are almost the same? And if I can do this mapping efficiently and this mapping isn't too big, then I can do this basically in linear time in the size of the data instead. So in particular, what we'd like is like a relative error bound. So I want a relative error with this mapping. And so it turns out the key question is the amount of time it takes. Think of Johnson-Lindström's lemma. I can start with the infinite dimensional space or whatever it is, or a really high dimension map down to 1 over epsilon squared dimensions. I can do that here again, and I can get relative error. So I suspect I should be able to do this here also. So that's the main goal. How fast can I do it? I can always compress it later. Turns out I need at least one of these 2 assumptions. Either I need some diameter bound in the space, or a minimum distance and a small additive error. So I need at least one of these. We'll use both, and all techniques basically use both of these assumptions. So previous work, so Rahimi and Recht in a test of time paper from Narips from more than 10 years ago showed you can do this with additive error, epsilon additive error, but to do relative error, you need a 1/alpha squared term, which is pretty big. And then a few years ago, there were some improvements, but they have a log 1/alpha error, but this is exponential in D. I showed a few years ago that you can recover basically JL bounds with the old features, but they only for single point sets with no additive error. So in this talk, we show, just basically announcing that for small d, we can do it so the time only has a logarithmic term in 1/alpha that's separated from the 1/epsilon squared term. And for high d, we can make it so it's linear in d and still logarithmic, still polylogarithmic in 1/alpha, and the 1/epsilon squared term is still there, right? As is required, and then you can reduce these back to 1/epsilon squared with JL on top of that. So okay, so these are the main results. So kind of we've removed the exponential dependence on d when getting logarithmic dependence on 1/alpha, which is much smaller than 1/epsilon. So just quickly for just a minute or so, just let me tell you basically what are the techniques. So the first is this key observation, which in retrospect to me looks very obvious, but I didn't see it for quite a few years, is that you can write this squared kernel distance function as actually the sum over these inner product terms if you put some coefficients kind of cleverly here. This means I just need to get relative error on the exponential part of the kernel. I don't need to do some similar sort of analysis as you do with JL, where you're looking at the distance. Then, if you're looking in 1D, you can do this nice Taylor approximation of this Gaussian kernel that's basically expanding the two terms from X and from Y. So those are expanded independently. So then I have an inner product between, if I define Vx and Vy as the appropriate part of these expansions, I can do these like separately. And in one dimension, this requires I can truncate the Taylor expression after roughly log 1/alpha terms. And this gives me the sort of balance I'm looking for. So then to go to high dimensions, we have to, this Taylor expansion is more complicated, involves the cross-vector terms, and there's this idea of this tensor sketch by Pog and Pham, and there's a new analysis by Alva et al. And Soda, and so we basically kind of, I think in the process we kind of reinvented analysis, but it basically is basically the same as theirs. And so if we apply this on this Taylor expansion with this view, and we do some extra calculations, we can put everything together and get these bounds. So great. So I'll stop there. So
thanks. Yeah. So are there any questions? We have time for maybe one quick question. You can either ask in the chat or just unmute yourself and ask. Okay, so if there are no questions, let's thank Jeff again. Thanks.
So thanks for organizing.
Yeah. Great, and yeah, and thanks also to all the speakers in this session. So now I guess we have a break until 11:20, so 20-minute break, and then we'll be back here for the last session of today. So see y'all in 20 minutes.